So in this screencast on alcohols from carbonyl groups, we're going to look at the basic functionality of a carbonyl group and the different functional groups that it's embedded in. We'll talk about oxidation state number and then the synthesis of alcohols from carbonyl containing functionalities. So as a review, what is the carbonyl group? So the carbonyl group is a carbon doubly bonded to an oxygen, and typically you have two other substituents bonded to that carbon, and then you have two lone pairs on the oxygen. So overall, recall that that's 1 degree of unsaturation due to the pi bond. The carbon is typically sp2 hybridized. The bond angle is 120 degrees for an sp2 hybridized carbon. And what is unique about the carbonyl group is we can draw a resonance form. So this double-headed arrow here, that's a resonance arrow. And if we do that, we keep track of our lone electron pairs. We see that the carbon has a formal positive charge and the oxygen a formal negative charge. Why is this resonance important for us? Because it basically is telling us that the carbon is electrophilic, so nucleophiles can attack it. And then the oxygen, basically, as we see with this arrow, can accept a lone pair. So we're able to attack with a nucleophile, break this pi bond, and then the oxygen accepts the lone pair. So that sort of indicates the bond polarity. So if I redraw the carbonyl group, so we see oxygen's delta minus, carbon's delta plus. So there's the bond dipole. And so that indicates the polarity of that bond, meaning that a nucleophile can attack the carbon because it's electrophilic. So let's review functional groups with the carbonyl pi bond. So I'm going to present these in a manner of referring to them according to oxidation state. So if we start off with this molecule, this is an aldehyde. This is a ketone. So again, R, R1, R2, those are just very general groups. We're going to assume that R is carbon, and this is an aldehyde. R1 and R2 can be the same or different. As long as they're both carbon, then this is a ketone. And so I'm going to start referring to oxidation state. Of the carbon bearing the heteroatom. Now, a heteroatom is anything that's not carbon or hydrogen. So in this example, the oxygen is a heteroatom. By oxidation state, all we are simply doing is counting the number of bonds from the carbon to the heteroatom. So we have 1, 2. Here we have 1, 2. So I'm going to call these oxidation state 2 functional groups, aldehyde and ketone. And the reason I'm keeping it simplistic like that is simply so that we can count to determine if an oxidation or a reduction has occurred. So let's draw a line and look at other carbonyl containing functional groups that are at a different oxidation state. And so these are going to be ones we study in Module 2. So the carboxylic acid, notice now we have 1, 2, 3. So these are oxidation state. Three functional groups. This is an ester. This is an amide. And this is an acid chloride. So what I want to show below each of these, because they all have carbonyl groups, is their IR signatures for the stretching of that pi bond. So IR is typically used to identify functional groups, and since all of these have carbonyls, they're all going to have that carbonyl stretch, but they occur in slightly different regions, and so you can use that to differentiate them. So again, the unit for IR is reciprocal centimeters. An aldehyde typically occurs from 1690 to 1740. A ketone, 1680 to 1750. The acid, 1710 to 1780, the ester 1735 to 1750, the amide 1630 to 1690, and the acid chloride is usually right at 1800. So there's other things that we can know about these functional groups to help us differentiate them. So this CsP2H stretch, again, that typically occurs lower than a normal CH stretch, so usually around 2750 to 2850. So if you see this paired with that, you can rule out a ketone there. The acid, again, you have the broad OH stretch, 3500 to 3000. That's indicative of that OH. Notice that the ester stretch is a little bit higher than your normal aldehyde or ketone. The amide is lower, usually below 1700. So we'll talk about that as well. That's important and why that's lower. And then due to induction, the acid chloride is the highest of all of them, and that's usually at 1800. So I want to revisit this concept of the carbonyl group being attacked by nucleophiles. So throughout this module and the next one, we're going to look at different types of nucleophiles that can react with these different oxidation states to do essentially either a reduction of the oxidation state, or it can form, keep the oxidation state the same, but then you're ending up with a functional group equivalent. So let's look at two types of nucleophiles here first. One is the hydride anion, so H minus. So for example, if we're looking at R1, R2, say we have a ketone, by inspection, we count the ketone is at an oxidation state 2. We're then treating that with H minus. We saw from above minus. This is electropositive. This is electronegative. So if we draw an arrow, the oxygen now bears the negative charge. So notice what we've done. We've added a nucleophile. We've changed from sp2 to sp3. We have 1, 2, 3, 4 sigma bonds now. Most importantly, if we count the number of carbon bonds to a heteroatom, it's just 1. So we're now at an oxidation state of 1. So 2 to 1, that's overall a reduction. Notice what we've gone from a ketone now to an aldehyde, or excuse me, an alcohol. So we can use this oxidation state number associated with the functional group to help us determine or predict the reactivity. So this is essentially addition of H minus. We can also add carbanions. So I'm going to write this as R minus, just so we can conceptually see what's happening. And then over the course of the lectures, we'll talk about what is the metal cation that balances out this charge. So if we're looking at sort of the same scenario, we'll call this R3. The lone pair will attack the sp2 hybridized carbon. We break the pi bond. Those electrons go onto the oxygen. Again, you can see that we're starting off, if this was a ketone, oxidation state 2. We end up with oxidation state 1. So ketone is reduced to an alcohol. And then, since these are all 3 carbon atoms, this would be a tertiary alcohol. So what we'll do over the next couple slides here is look at what are the specific reagents and solvents we would use to carry out this transformation. If we're using hydride or carbanions, how do we generate carbanions? What solvents do we use? What about functional group compatibility if we have acidic protons? So we're going to spend some time talking about that, where overall we're doing a reduction. And so these are specific examples with oxidation state 2, but what if we had oxidation state 3? What happens then? In this slide, we're going to talk about the oxidation reduction ladder. And so this is where we're going to look at functional groups, count the number of bonds to the heteroatom, which is defined as the oxidation state, and see how oxidation and reduction are related to one another. So I'm going to go ahead and use the general R group. And I'm going to start by showing this methyl group. And so this carbon we're going to focus on right now is sp3 hybridized. And I'm going to say that that carbon is at an oxidation state equal to 0. And so if we oxidize that carbon, which I'm going to show in square brackets, that being oxidation. And what we're going to learn are the reactions or the conditions that actually do that. We've actually seen some of it. So if we oxidize that, we're going to add a heteroatom, and we'll see that the hybridization stays the same. So the heteroatom we're going to add is just make an alcohol. So what we see is we start with CH3. We've oxidized it, so we've made a primary alcohol. We have one bond to carbon. Now we have 2 hydrogens. So that's an oxidation. So you'll note that this carbon is still sp3 hybridized. We have one bond to a heteroatom. That's where we're getting this 1. So we're going to call that an oxidation state 1. And this is clearly a way of learning functional groups and reaction conditions. So I said this was an oxidation reduction ladder, so you can actually reduce that back down using some set of conditions. And I'm going to put an H in there to signify reduction. So if you're going from an oxidation state 0 to 1, that's an oxidation. If you're going from 1 to 0, that's a reduction. Now, if we further oxidize this carbon, you're going to see we remove the elements of H2. So we remove H2. This gets a second bond or a pi bond between that carbon and that oxygen. So the oxidation state goes up to 2. So now we would call this an aldehyde functional group. Notice as well the hybridization at this point changes. It's sp2 hybridized. We're counting the bonds, so we're in an oxidation state of 2. So 1, 2. So it's a carbonyl. If we do a reduction, we go back the other way. So we're going to look at some conditions to do that specifically as well. So again, oxidation, we're going from oxidation state 1 to oxidation state 2, so alcohol to carbonyl. We can specifically oxidize this carbon up of an aldehyde, another oxidation state. So at this point, it would become a carboxylic acid. So we're counting 1, 2, 3. This is oxidation state 3. Notice the hybridization of that carbon remains sp2 hybridized. So you can also do the reverse as a reduction, where you're going from 3 to 2. So anytime there's an increase in oxidation state, that's an oxidation. Anytime there's a reduction in that number, it's a reduction. So depending on what the R group is, so if R was hydrogen specifically, so I'm going to write that here. If R equals H, this could be oxidized one step further. And basically that would get you carbon dioxide. So notice now we've changed the hybridization. It's now sp hybridized. We're at 1, 2, 3, 4, oxidation state 4. And really that's a special case where R is equal to H. So sp hybridized. This could be reduced. So we're going to spend a lot of time in this this semester looking at this oxidation reduction ladder. So conceptually, if you understand this, what we are going to spend time is looking at reaction conditions at each stage which affect these functional group transformations. So let's go ahead and start looking at first some reduction conditions. These are probably the easiest to understand and the easiest, I guess, I don't want to say memorize, but make an association with reactivity, because we're going to run into different functional groups are affected by these reagents differently. So let's go ahead and look at reducing agents. So we're going to look at two of them. This first one is called sodium borohydride. So Na plus BH4 minus. So cation, anion, this is a salt. Boron is normally trivalent, so when it has an extra valency, it's negative. So boron wants to get rid of hydride. So you see it in the name there, hydride. It's providing H minus. So another reducing agent that's commonly observed is called lithium aluminum hydride. So we have lithium Li+. Aluminum is right below boron, so it's AlH4. So the aluminum is negative. Again, it's a salt, plus, minus. They balance each other out. So sodium borohydride is typically, it's a solid, and it's usually a white powder. It's a bit hygroscopic, meaning it takes on water. It gets a little sticky when you're weighing it out. Lithium aluminum hydride is a solid as well. It has more of a grayish color to it, so gray powder. Lithium aluminum hydride is usually supplied in a very fine powder, so when you're weighing it out, you sort of see it sort of aerosolizes in a sense. This is more of a sort of a granular powder. So there's two reducing agents. What is important to know about them: sodium borohydride only acts upon oxidation state 2 functional groups. Lithium aluminum hydride acts upon all functional groups. So right here, we would say, because this only acts on oxidation state 2, this one is more selective than this one. Anytime this thing sees an oxidation state at 2 or 3, it's going to reduce it. So let's look at a molecule and see how these reagents act upon that molecule. So the molecule we're going to look at, I'm going to put it in the middle here, is difunctional. So we have an aldehyde and we have an ester. I strongly encourage you, anytime you see a structure, just go ahead and do what you know, write out aldehyde, write the word out. Ester. This helps you visually keep track of what's going on, because part of this semester you're going to be given molecules that are multifunctional, and then you're going to be given these reagents, and you have to know what functional groups those reagents act upon. That's called chemoselectivity. So say this way, going to the right, we're treating this molecule with sodium borohydride, and sodium borohydride is typically run in a polar protic solvent, such as methanol. So we said up here, sodium borohydride only acts upon oxidation state 2 functional groups. So when we look at this molecule, another thing we can do is just write the number. We have an aldehyde. This is oxidation state 2. The ester is oxidation state 3. So based on this knowledge, this reagent is only going to reduce this functional group. And it's going to do it in a one-stage oxidation. So let me write that up here. I'll write one-stage reducing agent. And so what do I mean by that, one-stage reducing agent? This is at oxidation state 2. It's only going from 2 to 1. So we're going to add a hydride. That's going to reduce this aldehyde now to a primary alcohol. So the product that we get under these conditions is the following. Now we have an alcohol. You always classify your alcohols. That's primary. Here's your ester. That functional group is retained. Let's just show the oxidation state. That's 1. That's 3. So this is what I mean by one-stage reductant. It's going from 2 to 1. So what about alternatively if we treat this molecule with lithium aluminum hydride going this way to the left here? So now lithium aluminum hydride, because this acts upon all functional groups, this is very reactive. Sodium borohydride is less reactive, it's more selective. Because this acts upon all functional groups, we actually have to use a different solvent. So the solvent we typically use is either diethyl ether or tetrahydrofuran. So either ethers. And this requires, so then when the reaction's done, you have to do an acidic workup. So these are, you take your substrate, dissolve it in the ether to make a solution. Then you can add this in as a powder to do the reduction. Then you monitor it by thin layer chromatography. When it's done, you add the acid. This reagent, I'm going to say multi-stage reducing agent. And so what do I mean by that? So a 2 goes to 1, a 3 goes to 2, goes to 1. So we'll see that in terms of the ester. So what you can do before I even draw the product here is predict what these functional groups are going to end up as. We already saw over here sodium borohydride, the aldehyde becomes a primary alcohol. So that's going to be the same thing that happens with lithium aluminum hydride. But maybe pause the video and see or predict what you think is going to happen when lithium aluminum hydride acts upon this. What functional group are you going to get? So if you've now unpaused the video, we'll draw that product again. The aldehyde becomes a primary alcohol. The ester is actually going to be reduced all the way down to the primary alcohol as well. And again, it's going from 3 to 2 to 1. So right now at 3, it's an ester. At oxidation state 1, it's a primary alcohol. At oxidation state 2, the intermediate, it's an aldehyde. So this reagent is so reactive, it does a 1-2 stage reduction when you're at this oxidation state. So let's put in those oxidation state numbers just to keep track. So again, that's 1 and that's 1. You know, all we're doing is just counting. There's 1 bond, there's 1 bond. And then we're identifying the functional group. So another thing you can think about, you know, as you're doing these predict the product questions is always ask yourself, you know, what do I think the carbon or proton NMR of this compound would look like? So if we take this one, What do you think how many unique carbon signals would you see for that? How many unique proton signals would you see? What would their ratios be? So if you look at this molecule, you have some symmetry to it. So in terms of carbon, this carbon and this carbon are the same, so that's 1. This carbon and this carbon are the same, so that's 2. Then you go out, these are the same, but they are also equal to this. So you have symmetry here, and then you have symmetry here. So you have 1, 2, 3 types of carbon. So that means you're going to see 3 signals in your carbon NMR. All of those carbons are all sp3 hybridized. We have a couple of them that are sort of the same in a sense, where you'll see them in the spectrum, but you have this one which bonded to oxygen, so that's going to occur a little bit further away from these two. So these two will be closer to, say, 0 to 20. This one's probably between, say, 40 and 60. Then in terms of the unique sets of hydrogen, you have 1, the OH. You have this methylene, that's 2. Methine, 3. And then these methylenes are all the same, so that's 4. So we can write 4. Then our ratios would be 2 to 4 to 2 to 2, 4, 6, 8. So again, as a review, this is the unique number of sets. 4, we have 1, 2, 3, 4. This number here, the total, we have 10, 16. That's the total number of hydrogens. And this is just telling you the ratio of those 4. So one last slide here to summarize reduction conditions. So we'll just visually show some functional groups. Again, I'm going to use R. So acid, this is oxidation state 3. Ester, again, oxidation state 3. Ketone, oxidation state 2. And then aldehyde, oxidation state 2. So as you see, we have four carbonyl containing functional groups. We've identified in blue number by counting 1, 2, 3, the oxidation state number. So here's sort of a trend, and we can say that because these are both oxidation state 2, sodium borohydride will only reduce those, whereas lithium aluminum hydride will reduce all of these. So keep in mind what we just said. Sodium borohydride is a one-stage reductant. It only takes oxidation state 2 compounds down to oxidation state 1. Lithium aluminum hydride, because these are oxidation state 3, they will proceed to be reduced through oxidation state 2. Then that will subsequently in the reaction be reduced to oxidation state 1. So we're going to look at the sort of how these different functional groups, when they're reduced to alcohols, what is the classification of the alcohol that is produced? So a way to think about this, let's just go ahead and we're going to make sort of a table here. I want to say primary alcohol. I'm going to say secondary alcohol. And through the method of hydride reduction, we cannot make a tertiary alcohol. So functional groups that will make a primary alcohol would be acid, ester, and aldehyde. So reagent, lithium aluminum hydride, lithium aluminum hydride, sodium borohydride. And so if you treat these under those conditions, they're all going to give you this primary alcohol. So again, oxidation states 3, strong reducing agent, 2-stage reduction, you get a primary alcohol. So we fall under this regime here. Oxidation state 2, 1-stage reductant, primary alcohol. Secondary alcohols can only come from ketones because those are the ones that have 2 carbonyl groups. So R1, carbonyl, R2, LiAlH4. So we would get R1, HOH, R2. So alternatively, taking the ketone and treating it with sodium borohydride will give you the same product. So again, even though lithium aluminum hydride is a 2-stage reductant, you're only starting at oxidation state 2 here, so it can only go down to 1. So lithium aluminum hydride or sodium borohydride will affect the same transformation to give you a secondary alcohol. And again, you cannot make a tertiary alcohol from the reduction of these functional groups just by the nature of you're adding a hydrogen to that carbon bearing the oxygen. So in this screencast, we've looked at the oxidation state ladder, some reduction conditions, and in the next screencast, we'll look at oxidations, where we're going from, we're increasing the oxidation state, so alcohol to carbonyl, or carbonyl to acid.